Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our D programming language series. In this lesson, we're going to be talking about the ampersand operator. Now, the ampersand operator gives us the address of something, whether it's a variable or a function, for example. And this is going to be important just so you understand where your memory is actually located. So this will be a brief continuation of the last lesson that we had here, so you can check out the D programming language playlist if you need, or just check out that previous episode. But with that said, I'll do a quick recap and then introduce ampersand to you. Now, last time what we talked about was this idea of a call stack. This idea that when we call functions, each of those function calls and any locals or the parameters that are created are stored in a special section of memory here. And we have something called a stack pointer that tells us which function is going to be executing. So for example, if I have main here, and let's go ahead and we've learned about previously, if you've been watching all the lessons in this series, we have arguments here. So that's a local variable. So we'd have args here, and any of our locals, things like result, for instance, would have to be stored in its own little call frame here, and the return address as well. So I'll just call it return, or RET for short. Let me just write it in quickly, and I'll put this in its own little box here just so you can see that it's part of its own activation context or frame here. So then when I call other functions like addition functions, for example, or the addition plus one function, which I'm just scratching in there, that again will create its own little frame here. When that call is done, then it'll be removed, and then we'll come back to the return address and be back to this particular location here. So that was the basic idea of what we covered last time. This special section here, it called our call stack or just our stack, that's part of our program representation. So again, when a program's executing, it has some notion of, again, what's actually being called, the functions, the local variables, what's in scope essentially between various curly braces or within those curly braces nested inside. But what I want to go ahead and talk about today and get to the point here is this ampersand operator. So what is this exactly telling us here? Now let me go ahead and get rid of my right line here. And instead what I'm going to do here is do a right line and do ampersand result. And let's just go ahead and run this program here. And this time you're going to see that I'm writing out this strange hexadecimal form, which is a number that you could figure out in decimal. But this idea is where exactly in memory is result stored. So wherever this location is here, and I'll just circle it here, this is the corresponding address in memory. Now, each time you run your program, this might change, but for this particular run, when it ran, this is where your stack happened to be based off of, how many programs are running in your machine. So that's the idea here, that we're able to query for the address. Now, something that I like to do here is, and that's useful, I found for learners, is just to go ahead and wrap result in parentheses here, so that you can think of the ampersand or address of as a function. Because that's essentially what it is. Just like if I was to replace this with plus is a function, minus, multiply, etc. It's just that the input is right after here. So anyways, that's the address of this variable here, this local variable. So let's go ahead and try this a few more times here. Let's go ahead and create an array. Here it'll be a dynamic array. We can create a fixed size array of 10 elements. So fixed size array. And let's go ahead and just create another array using something that's new to us. And I'll go ahead and just set up here. I'll say heap array, which we'll have to talk about. And I'm just going to allocate manually 100 integers here. Okay. Now let's go ahead and just print out each of these values, meaning the addresses of them. So the address of result we've got here. So let's go ahead and repeat this. Let's get the address of our array. Let's get the address of our fixed size array. And let's do this one more time and get our heap array. Now we haven't talked about this new keyword yet, but what I can tell you is that's allocating some space here in our memory here for this heap array. In fact, for our dynamically allocated array, this array here, that's also got some space somewhere in the heap. And I'll go ahead and show you this in just a moment here. In fact, just so that I can illustrate this, let's go ahead and just append an element here. Let's go ahead and append the number 5. just so that we actually allocate some memory here. Okay, so let's take a look at this program. Let's go ahead and run it. Make sure I didn't make any mistakes here. Oops, looks like I made one tiny mistake. I always sometimes miss a key here. For append, we've got the tilde mark. And there we are. Okay, so what are the important things to see from this ampersand? Well, again, we're getting the addresses of these variables here. Again, for result, array, fixed size array, heap. And what you might notice, which is kind of interesting, is they're all relatively in the same location. Meaning this value here, and I'm just sort of looking at the least significant digits here because all the first ones are the same essentially, other than here. This one's at 60, 70, and then I come here and I allocate 10 actual elements here for my fixed size array. And then I have another offset here for my heap array. But these are relatively the same locations. So what I'm just trying to show you is that all of these variables here, anytime you create a named symbol here, those are being stored in your stack. They're nearby each other somewhere here. And I'll just go ahead and write them out here. I've already written out result here, but this is all part of the same frame here. So we've got our array, fixed array, and heap array. And these are basically just ways to hold how to get to the next actual information. Meaning that, well, for this heap array here, I've got 100 integers, but they might not necessarily be stored here in this stack. Now, maybe there's optimizations and stuff that might place them here, but as I mentioned before, they're stored somewhere here. So how do we figure out those addresses? Well, let's go ahead and try here. Let's go ahead and write out the address here. And in order to find out where the actual data is, let's go ahead and try our array, the first element here. So to figure out where this actual 5 is stored. And let's go ahead and try for our heap array here. Heap array, and we'll just look for the first element here. Now, what this experiment is going to show here is that if our data is stored elsewhere, or maybe in a far off location, maybe that's just going to prove again that there's separate memory locations for heap allocated data and stack allocated data. Okay, so let's go ahead and run this. And I'll go ahead and run here. Oops, and of course, made a little mistake here, missing some parentheses. And that should fix it. There we are. Okay. And well, what do we see here? Well, if you kind of look at these numbers here, I see F032 versus FFFA here, FFFA, FFFA. And this F, again, there's some offset. Now, these aren't the same values. They are separated here. But again, that's telling me that my heap is somewhere, and I'll go ahead and just label it on our diagram, in 7, F032, C85, 100 maybe, or for our heap array that I'm specifically printing out, it's at 200, so I'll be correct, and then the array is some other value. And typically we put 0x in front of hexadecimal things. And our stack pointer is somewhere 0x7FFFA, and you get the idea that these are different offsets in different locations in memory. So that can be useful for us in a sense of just using this ampersand operator for knowing where stuff's located. Now, pragmatically, often what you'll do is actually try to figure out, is this the same memory with the ampersand operators? So for example, if I have two variables pointing to the same location, you could use the address operator to figure that out. So that's a little bit of a continuation with our heap and our stack conversation in this idea of a program stack. But what I also want to talk to you about is, well, everything has to be stored in memory, right? There's this other section down here, our text and our source code. So what about our functions, like addition plus 1? Well, a function must be in memory. It's in our source code. So where is that? So let's go ahead and just take the address of addition plus 1, this function. And just to make things a little bit easier here, let's go ahead and just give ourselves a little bit of padding here by putting some empty right lines here. This is something that I like to do. But let's again go ahead and see where addition plus 1 is. And if I go ahead and run this, oops, I guess it wants some input here. Let's just put an empty string. There we are. Oh, and I'm missing a semicolon here. Okay, I actually don't think I need the empty quotations, but I'm going to leave them in there just so you can see here that, again, in a totally different location. So 55 something, I'll go ahead and label this probably in our text section, 55 FF. Now this could be separated out into various tables and other organization, but I'm just going to put it down here for our function. 5, 3, 5, 6, 8, C8, etc. So again, that's just showing you that, well, functions have addresses. So that's kind of interesting if we know where an actual function is. So in theory, we could actually call this function by just activating some address and then passing in some parameters to that address. And we're going to talk about that with an idea of function pointers and some of these things that we can do in the D programming language. For those of you coming with a C or C++ background, you already probably know where I'm going here, where I'm going to be talking about pointers eventually in this series and where they fall into the D programming language. But at the very least, as a tool, I just want new programmers to know that we have this ampersand operator. It tells us where stuff is. And if we think just a little bit about what the actual stuff is we're storing, we can try to figure out if it's in the stack or the heap to tell us, is it something temporary or is it something in this other heap section of memory, which we've yet to talk about, that's going to be long-lived or maybe has some other purpose. All right, folks. So with that said, I hope that was a useful lesson. I hope that sort of is putting things together. At the very least, if you're coming from a programming language like C or C++, you know we have ampersand and we're good to go. And again, if you're sort of newer to programming or if this is your first programming language, I just want you to know that ampersand means address of, and that we're able to find the actual memory location of where something lives. With that said, if you have any questions, feel free to post in the comments below. Make sure you subscribe as we're really gaining some steam in this series, and I'm going to have a lot more cool stuff to talk about. So I hope to bring you along with that journey. And as always, thank you for your time and attention, and look forward to seeing you in the next episode.